All right, let's do another one. So tonight, our second problem of tonight is going to be number 98. Validate binary search tree. Given the root of a binary search tree, determine if it is a valid binary search tree. And we have the standard criteria of ABST. So what could we do for this? The simplest solution that we could do is we could run a, what is it called? We want to run a in-order traversal through the tree and build up an array of sorts. Or actually, we don't even really need to build up an array of sorts if we do this iteratively. And keep track. No, but there could be a... Oh, this is a good question. Because the problem is that, okay, we can run an in-order traversal through the tree iteratively, right? This is fine. Then the question really then becomes, how do we check to make sure that each element is where it should be without making it too... Sorry. Without making it too slow. We could... The first thing that came to my head was, could we just do a sliding window of size 2? Comparing against previous neighbor. Basically, if the number is smaller than its neighbor, then it doesn't make sense. Or in this case, it would be previous value, right? And if it isn't larger, then, or sorry, if it isn't larger, then we know something's wrong, right? So if we do like 1, 5, then 4, well then, or 1, 5, then 3. Is this valid? Let me think. 1, 5, then 3. One 5 is valid. 1, 5 is valid. If this was 6, no, because 3 should have gone to the left and then to the right. So this is incorrect as well. So I think, I mean, it makes sense for it to be here, to be to the left of 4, and but I'm not sure relative to the left subtree contains nodes with less than the nodes key, or the nodes key. Yeah, the right subtree contains only nodes greater than the nodes key. Yeah, so this is the left subtree, this is the right subtree. The 3 should not belong there then. And of course the 4. So in this case, if we do a BST traversal, then we should receive an array that is strictly increasing, never decreasing. So I think we could do a sliding window of size 2, though I'm not entirely sure. Because it is very much possible also that if we had like a 9 here, right, it would be 1, 5, 9. The only way we could detect that is that if we had 1, 5, then our sliding window becomes 5, 9, which is fine. Then 9, 4, which is not fine because then we're decreasing. So I think a sliding window size 2 could work. I might have to double check that though. In any case, we will do a var previous value is equal to, and because the range of the nodes is within 32-bit integer, I think. -2 to 31. I think that's min ins, yeah. I think that's min value. So we can have a int nullable first, which is a little bit stinky, but we'll deal with it. We can do a, let's see. We're going to need a queue of sorts. We can use a mutable list TreeNode. We can put our root in here. And if our root is null, or how many, the minimum number of nodes we can have is 1, right? So if root dot left is null and root dot right is null, then we can just return true. So this is like our not quite edge case, but we'll deal with it like that. We can say while q dot is not empty, we will say our front value is equal to q dot first. And we can also say q dot remove at 0. So this will just cycle through the elements. And actually this should actually function more like a Is there a way that we can actually do in-order DFS or in-order traversal in an iterative manner? Or is there a way that we can do this in a manner that is, we can say fun is valid BST, so we do an overload, and then we can say previous value, which is an int, which is also a boolean. We can say if root.left, then we can say var is left valid starts off as true, var is right valid also starts off as true. Is left valid is going to be equal to is valid BST for our root.left, and our previous value is going to be our current value, so our root.val. If root.right is non-null, is right valid is equal to is valid BST, root right root val. Then we just compare return is left valid and is right valid, and or we can do the first one, root.val is less than previous value. So the idea is that we will go to our left as far as we can, and we will pass our 5. So we pass our 5, and then we go to our 1. Now this 1 has no children, so it will return left valid, right valid are both true, and is our root.val, our 1, less than our previous value, which was 5, and that is correct. We will also go to our right side and do the same thing there. Now this will call our left side and right side, which is correct. However, when this 4 comes along, this will return root.val is less than previous value, but our previous value was 5, and that will not be the case. The problem then becomes we need to make sure that we're not colliding less than the node's key. We need to make sure that we are not calling this on the root. The problem is, how do we identify the root? Well, we could be lazy about it and we can create a third-party reference or an outside reference to it. So we can say val root or var solution root is of type TreeNode nullable is equal to null. And we can say if solution root, or if root is equal to solution root, return true. And then we can say return is valid BST on our root with a previous value of -1. Or actually we can just say root $.val. Doesn't really matter. It shouldn't matter because we do that. Well, we need to set the solution root is equal to root first, right? And then we call this on the root, and then the root.val. So basically it checks the left side first to make sure that it's compliant. Then it checks our right side for compliance, and then it checks us. So this is actually not in order traversal, this is a post order traversal, because we check our left, then we check our right, then we check our actual node. Though I don't think the order of the traversal that you run actually matters too much here. Let's give this a shot. I have a feeling that there is a corner case that I'm missing here, but we'll think about it some more as we run through this. TreeNode ? It's not null. It's not null. Okay, cool. Root is not null, and so this should hopefully make the compiler smart enough to realize that this cannot be true beforehand. Okay, 213 worked. Let's check 514 null 36. Looks like this went wrong, unfortunately. Let's see. We can say print line comparing root.val against previous value. So it should be 1 against 5, 3 against 4. Let's see. Doesn't look like that actually even gets called in the first place. That's weird. Why isn't that getting called? Oh, it's because of this. Okay. Right. It's either this let's see. It must be this and a combination of this. But our root is not always our solution root. And are there duplicates? There may be duplicates allowed. How should we do this then? Essentially, the main blocker at this point is that we cannot, or we should not, do the comparison thingy with less than or equals to. Or we shouldn't, we don't really have anything to compare against our root. But we could try our less than or equals to, and then let's see how that goes. Once again, this is, for some reason, not fire. Oh, because we never got rid of this. Let's say that we get rid of the solution root thing altogether. And let's see where that takes us. So 1 against 5 works, 3 against 4 works, 6 against 4 does not work. That's not quite true. If, let's see. Previous value is like that, right? It's not quite true. Then we actually want to do val. We want to process the middle one here. Val is center valid is equal to true. That's awkward. We can do a parent, which is a TreeNode. If if parent.left is equal to root, is that else root.val is greater than or equal to previous value. So the idea is that if our parent left, so if the parent value that we came from we can just get rid of that altogether, honestly. So we just run with the parent instead. This previous value, parent.val, or question mark dot val, parent question mark dot val, then okay, no more previous value, so we just pass in our parent, so they know where we're coming from, and if we're coming in on the left, then we make sure that's less. If we're coming in on the right, then we're making sure that we are greater. Inferred type is int. This is in parent question mark dot val. Val is center valid is equal to, if parent is null, or parent dot val, if the parent is null, then it's true. If it's not, or yeah, if it is not null, then we say if root dot val is less than, or if parent dot left is equal to root, then it's root dot val less than or equal parent dot val. Otherwise, root dot val is greater than or equal to parent dot val. And I'm assuming that this should work. Looks like root is still having trouble, like root is null. Shouldn't need to deal with this now, because root should be null. or root should be non-null. Okay, so now we can sort of simplify this center logic by saying is center valid. Unironically, I am exhausted. I have no idea why. Okay. And actually this works even better because now when we compare 5 against null, well, it's 5, we check that the parent is null, so we don't do anything there. So 1 against 5, 3 against 4, 6 against 4, 4 against 5, 5 against null. So 5 against null, of course, that's fine. 1 against 5, that's fine on the left. 3 against 4 on the left, that's fine. 6 against 4, that's fine, that's on the right. And 4 against 5, that's you can print line is valid status is left valid is center valid is right valid. So this should be 1 against 5, true, true, true. 3 against 4 is fine. 6 against 4 is fine. 4 against 5 is not fine in the center because we're on the right. And that propagates up. Cool. So, this is fine. This runs in O of n time, where n is the number of nodes in our tree, because we have to compare we have to essentially compare the node to every parent within our tree. However, I'm not sure if this will actually still work if we throw in the context of what if we have a solid subtree that just so happens to be connected through a bad branch. And what I mean by that is that this probably doesn't work if we just propagate up, because of the fact that it might be fine for one layer but not for the next. How do I describe this in graph form? We have 5, 1, 4, 3, 6, right? And 4 is the problem here. But let's say that this was, if this 5 was a 2, that would be fine. Is it true that in any case, if something is wrong in one place, that it'll show up at the root level? Let me think. If I had a large number here, that had a smaller number up on the 4, would that work? Would that hide it? I'm trying to think of an example where it would be hidden, because I feel like it exists. Where a tree of this size works perfectly fine, and a tree of this size probably also still works fine, but something about this tree in comparison to the root, like a sort of imaginary root over there, that makes it not fine. I think I can think of an example. Let me see. If I did, on the high level, I did 3, then I did 1, 5, then I did null for the 1, then on the 5 side, I did 4, 6, Then null, null, 1, 2. Where do those end up? Okay. They end up there. Right? And this could be like a 10, it really doesn't matter. And this could be like a 7. That's fine. So this is a perfectly valid tree for now, right? 3, 5, 4, and then 6. And then actually no, this should be like this should not be a number that is that small. Let's do 7 here and 6 here to make it valid, right? So this works. However, if I do something like these numbers are way too close together. I'm gonna set this to 8. I'm gonna set this to 9. It needs to be bigger than this node, but it smaller than this node? Yeah, okay, in that case I'm gonna make this one null. Actually, keeping that 1 there is fine. We just need you to be like a 7 or something, right? Or we can have you be a 7. You need to be less than that, so let's have you as like a 3. 3, 1, 7. It's be larger than this, but smaller than this. But if this is larger than you, if you are larger than you, and you are not picked up, and this change is not propagated up here, that means you must be larger than, sorry, you must be larger than you but smaller than you. But if you are smaller than that, then that means you because you're smaller than that node, then you should be smaller than that. So I think actually this probably works fine. I don't think that there is actually, maybe there is and I'm just dumb, but I'm just gonna hit the submit and let's see. Let's like actually get like a concrete example from LeetCode if there is one on sort of a bad example that just an edge case that just murders this approach. 222 is not valid. Okay, so in that case, we cannot have duplicates. Cool. Okay, that's fine. We do less than and we do right then. And if we do 222, how far did we get in the test cases before this? 62 test cases passed. Okay, that's impressive. But there's probably some more edge cases that will probably screw us over. Let's comment out these print lines because we don't need them for now. And let's run this again and let's see where we end up. Cool. I think this is actually a case that I was talking about that I couldn't think of on the spot. Because 3 and 7 are fine relative to 6, but are not fine relative to 5, and therefore this binary tree is invalid. However, because this binary tree does not get tested at multiple levels, then this incorrectness does not get propagated through. Right? However, what we could do is that the minimum of this center value here should be greater than the minimum of this this left subtree, right? And it should be it should be less than the minimum of this subtree, and the value here should also be greater than the maximum of this subtree. So a naive solution would just be to find the min of, or the max of left, the min of right, and then compare them. But that's a lot of additional work. So what we will do instead is that we could try to think of a proper in-order traversal that is iterative, and then we can create this into an array. And I think that's how we will make it work. However, that still leaves open the question of how do we do this? Because how do we pick the minimum of the max of the left side and the min of the right side efficiently? Because we could just run it on the algorithm to find the min and the max to just do essentially an O of n-1 search on each side. But that would not be efficient. This would be an O of n squared solution essentially, because this would need to run O of n-1, O of n-1, and then O of n-2 times O of n-2, and then 4 times n-3, and that might actually be 2 to the n of a solution. I could be wrong on that, but that sounds like a 2 to the n solution, because we're calling on it every single time until we get down to 1, and we multiply it by 2 every time. So yeah, that doesn't sound maybe solution. We could sort. And the value in sorting is that if the order of any element changes, then we know that the BST is invalid if we do a proper in-order traversal. This is an O of n log n solution, but I think we can still do better. But the question really comes down to how. Because we need to compare a singular element against all other elements, right? We need to compare that when we run a binary search tree like this. We compare the 4 against the 5, but we also need to make sure to compare it against the 3 or the 6, 3, and the 7, right? Because if the 4 is larger, is there a rule with binary trees that we could use here in order to make life easier? I think I'm going to go try to track this down in cracking the coding interview, like I've said, and try to get a hint for this, because this is starting to take a little bit long and I don't have time. Okay, I'm just running some tests against our previous values, our previous examples and stuff like that. So I think the lesson that I learned here, and I just took a look at the cracking the coding interview hint, is that the in-order idea was correct. However, the main lesson for this case is that if a value needs to be held for more than one layer within an in-order, pre-order, or post-order traversal, if a value holds, or if something holds for more than one layer, i.e. just between sort of the previous node and this. So for example, within this pre-order traversal, we need to compare this. Let's just take this tree, for example. We need to compare this 3 against not only the 6, but also against the 5, right? The 5 that came before. But how do we get that 5? Well, we could use a global state in this case. There's probably a smarter way to do this that doesn't involve global state. But as far as I'm concerned, this seems to work decently fine for now. So let's give this another submit, and then let's see sort of where we end up now. I'll have to definitely come back to this and see if there's a better way to do this without global state, because I'm not a fan of declaring like things like this. Within an online assessment, I think it's fine, but I think generally you want to avoid having a state like this. It just makes things messy, right? And in this case, I'd probably do like last val is equal to null first, null it out before every operation in order to make sure that we don't get any leftovers from the previous call of this, right? So let's see. I think that's pretty much it. It's pretty much the same logic, but we just take this last value instead. I think I was doing something similar actually with the first approach, or the first thing that I attempted, but I'm not sure. I don't think this is something that can recurse well. Would it recurse well? Let's see. If I do this, it'll go 4. Then I would call it on the right side with this previous value. And then I call it on the left side. Well, if I call it on this side, do I call it with the 6 or do I call it with the 5, right? It's an interesting thing to think about. Perhaps something to revisit in the future. I just wish I wasn't so damn tired today, so that I could do some more thinking about this. In any case, it looks like we did all right, and I'm just going to leave it here for today. I apologize for being pretty dead on this, but that just happens sometimes. In any case, I hope you learned something, and I'll see you for the next problem.